Welcome to this first video on continuous time systems. Up until this point, we've been talking about continuous time signals and signal classifications. Now we need to cover some of the same ground, but talking about continuous time systems. So in today's lecture, what we want to consider is, what is a system? How do we describe systems using system operators? And how do we classify systems into different types of systems? So to begin, what is a system? Well, the simplest way to depict a system is with a black box, a simple input-output relationship, where the system is what's inside the box, input is the signal coming in, output is the signal coming out. This would be a block diagram representation of a system. A system represents a mathematical mapping of all the elements of an input set that we'll call X, and the output set we'll call Y. And the system provides the mapping, the connection between the two, the way that we take input values and turn them into output values. And so the standard way that we describe our systems with what we would call input-output formulations, where our input is traditionally, we'll use X of t for the input signal, Y of t for the output signal, and recognizing that both of these are probably time-varying functions. The system then is described by some kind of formula. It tells us how do we take values and sequences of values coming in on the input and convert them to values and sequences of values coming out the output port. In the notation shown here, we're using a squiggly S to represent the system and the operation it does. This symbol S represents the system operator. This is the description of the dependence of the output signal, Y of t, on the input signal. And so S captures this input-output relationship provided by the system. With this system operator description, we don't necessarily need to know what's going on inside the box. It could be made up of electrical circuits, it could be made up of mechanical subsystems. The system operator describes for us the mathematical relationship between the output signal and the input signal. And so we don't need to know the internal makeup of the system. We just need to know how it behaves, how it influences signals. Now, there's an alternative formulation that instead of describing the operation of the system just in terms of input signals and its connection to the output, there are also what we call state variable formulations. Here we describe the output as a function not just of the input signal, but the input signal and some internal states of our system. So it describes how the output signal is created from the input signal and some changing internal conditions, which are represented by these state variables of the system. These states, these internal states, are the minimum amount of information that we need to completely characterize the system at any instant in time. Now this sounds strange, but you've actually encountered this before. Back in your first digital design course, you worked with two different classes of digital systems. You worked with combinatorial logic systems, and you worked with state machines. And with your state machines, you would describe how the system operated by moving from one state to another. And the variables that described each state were the equivalent of our state variables here in our state variable formulation for systems. Mathematically, our system operator S tells us how we produce a new output function, Y, from any or all values of the input function X. We get the output at any given time, t1, and that output, that value of y at that instant t1, may depend on values of the input arriving at time t1, or possibly prior to that, or even possibly after t1. Right now we're not placing any restrictions on our system operator and its characteristics. Here's an example of a system operator. If we said the purpose of our system was to estimate the slope of the input signal, so y of t should represent the slope of the input signal, x of t, at all times. Now you might jump to say, well, we should create a system that computes a derivative. Well, we'd like to do an estimating version of that. And so we'll do a little piecewise estimation of the derivative of our input signal. Instead of finding the derivative of the input signal with respect to time, we'll measure the change in the input signal with respect to a jump in time and use that as estimation of the slope of the signal. define the output at any given instant in time, y of t, we'd want to know what's the value of x just before and just after this moment in time, subtract the 2, and divide that by 2. So for example, y at 1 seconds could be estimated by taking 1/2 of the input signal at time 2 seconds and subtracting off the input signal at time 0 seconds. Now in this case, we have a signal whose value is determined not just by the current value of x or a previous value of x, but in this case, a future value of x. Again, for the moment, we're allowing that in our system operators. A simple example of another system operator would be a system that provides amplitude scaling. This we would consider a simple ideal amplifier. So if whatever the size of x of t is, the output will be a scaled version of x of t. It'll be scaled up by a factor of c. So our system operator then takes x of t and multiplies it by c and produces a new output y of t. So whatever shape and size x of t has, for example one that peaks up at a value of a, would run through the system and produce an output y that was c times as big. So it would cover the same interval of time, but its amplitude would be scaled by c. Now what we need to do before we embark on learning some different analysis techniques for system analysis, some ways to characterize systems, is we need to classify them. Because the tools that we're going to be developing will only work with certain classes of systems. So before we even get started, it's important for us to be able to look at a system and its system operator or its describing equation and determine whether it fits in the category of the kind of system that our analytical tools are going to operate properly on. So we're going to want to divide all the possible systems that we might create with different mathematical operators into different classes based on whether or not they have certain properties. Namely, we want to be able to tell, is a system static or dynamic? Is a system linear or nonlinear? Is a system time invariant or time varying? Is a system causal or non-causal? Is a system stable or unstable? Now some of these terms you've heard before, and what we'll do now is define them in our systems context so that we're clear about what they mean, what they imply, and what are the properties that systems have that they fall in these various classifications. And how do we look at a system and its defining equations and tell whether or not it falls into one category or another? So we determine systems classifications by either applying the definition of the properties that should exist in a system if they belong to this particular classification, and we apply that to test their defining system operators. Or alternatively, we look at the defining equations that describe the input-output relationship of the system and look for certain characteristics in those system operator equations. Our first classification is determining if a system is either static or dynamic. Static systems are also called instantaneous systems, and that's a good definition for them, because if we're trying to determine the value of the output, y of t, at some particular moment in time, call it t0, that output signal y of t0 is completely determined only by input signals that are happening at exactly the same moment. So all we need to know to determine the current output of y of t is the current input, x of t. We don't need to know anything about what came in the input before or later. Likewise, we don't need to know what the output was later or sooner. All we need to know to find the output now is what is the input right now. We only need the present value of the input signal. An example of such a system would be one described by this equation. Y of t is a system operating on input signal x of t, where the system operator takes x of t, multiplies it by c, and adds an offset a. In this case, for any given moment in time, we can compute the output knowing just the current input. The way we determine from the defining equation whether the system is static or not is we look at all the time arguments. And if y of t and x of t, in whatever forms they show up in, all have just the same exact time argument, then it's a static system. Since we have y of t on the left, we have just x of t on the right, no time delays, no time compressions, no time shifts, and we add a constant, and that has no time functionality, and so it doesn't change this from being a static system. So for static systems, the previous inputs have no effect on the current output of the system. Effects of previous inputs don't linger around and don't affect the output anytime later. And so we say static systems have no memory. There is no carryover of previous events, either previous inputs or previous outputs or previous internal states, to change the output of the system to affect it. In our defining equation, not only are we going to look for time arguments that are the same in all the x's and y's, but we're also going to look to make sure there's no derivatives or integrals in the system equation. Think about integrals. They sum up things that happened from the past up until the current moment. And so if I have an integral in my equation that defines my output in relationship to my input, then that implies there's some previous things that are going on and influencing my current value. So I can't have those. In terms of derivatives, we can think of them again in the simple-minded approximation that a derivative represents a change in an input or an output signal. So in order to determine whether there's a change or not, I need two values. I need a current value and a previous value, or a current value and a future value, to determine what the slope is of my line or of my variable. And so having derivatives implies that I have some kind of previous or future information involved. And so static systems, instantaneous systems, cannot include either integrals or derivatives in their defining equation. The opposite of that is a dynamic system. A dynamic system does have memory. It can be described by equation that does include derivatives, does include integrals, does include time shifts, does include time compressions and expansions. I can need information from other instances in time other than the present moment to determine the output in a dynamic system. So determining the output at some time t0 requires either previous or future values of either the input or the output. If that's true, then I have a dynamic system. And again, dynamic systems have to have some sort of memory. Now, in our electrical circuits, if we're working with analog circuits, we don't necessarily have things we think of traditionally as memory, like computer memory. In our context, we would mean devices that contain energy storage, like inductors and capacitors. These carry over charges and magnetic fields that provide an influence, a future influence, on the voltages and currents in our circuits based on things that happened in the past. And since our circuits might contain not just resistors, but capacitors and inductors as well, they'll be characterized by differential equations, things with derivatives and integrals. So anytime we see an integral or a derivative, that introduces into our system the effect of previous signals. And so that's what gives rise to memory, in quotes, in our dynamic systems. Now again, a previous example that might help make this clear for you is again the digital example. So we had those two classes of digital systems that you were designing back in CPE 133. We had those combinatorial logic circuits that were static circuits. You used Boolean logic expressions to compute how the output signal was determined by just the current value of the input signals. When you arrived at state machines, you had digital systems where your jumping from state to state was determined not just by the newest input arriving, but by the previous state of the system or the circuit. And so we had some memory involved. In the case of those digital state machines, that memory took the form of flip-flops or actual memory elements or registers that kept track of the states of the circuit and how they behaved, what state they moved to next, what output they created, depended on what their current state was, which was a result of previous inputs, as well as what the new input was coming in. Those were dynamic systems. So again, the best circuit example we have for a purely static system is a resistive circuit. So if my input signal is on the left, and then is the input to this voltage divider with resistors R1 and R2. And if we let our input signal x of t represent the voltage, a time varying voltage coming in on the left side of the circuit, and our output is a time varying voltage on the right coming out, that's our y of t equals V out, then we know we can write a voltage divider equation. V out equals V in times R2 over the sum R1 plus R2. So our system operator, our output, V out, is equal to a fixed numeric ratio, R2 over R1 plus R2 times x of t. So we have essentially a gain equation here. There's no derivatives, no integrals, no changes in time arguments. So this circuit represents no energy storage. This is a purely static circuit. Now, a big system classification that we really need to understand well is the difference between a linear system and a nonlinear system. Mathematically, linearity involves two different properties that we can describe each individually and then put them together to create a system with the property of linearity. The first half of linearity involves a subproperty called homogeneity. A fancy name for something pretty simple. In operator notation, we would describe homogeneity this way, that if the system operates on A times x of t, it better look the same as if the system operated on x of t, and then we multiplied that response by A. Now, an easier way to look at this is in terms of input and output of signals. If I have a homogeneous system here in my red box, and I put in some input signal x1 of t, put some arbitrary shape in, and whatever this box is, if it's homogeneous, then it'll produce an output signal y1. If I then put in a new input signal that looks like just a scaled version of x1 of t, it could be amplified or it could be attenuated, but as long as it's multiplied by a scale factor, if I put that signal into the same system, whatever comes out better look like a scaled version of y1 of t, and the scale factor better be the same between x and ax as it was between y and ay. So another way of saying that, if we scale the input, the output has to be scaled by exactly the same factor. That's homogeneity. So multiplication by a scalar on the input affects the behavior of the system in exactly the same way. We get the same scale factor on the output signal. Additivity says if I put some arbitrary signal x1 into my system and see what comes out, call that y1 of t. And let me do that to a different signal. I'll put a different one, x2 of t, in that could be entirely different from x1 of t. Doesn't matter. Here they're similar in appearance, just to make the drawing easier. If x1 of t produces y1 of t and x2 of t produces y2 of t, then if I take a third test and put in an input signal now called x of t that's created by adding up x1 and x2, so it looks like the sum of those two signals, we put that into our system, what comes out, y of t, better look exactly like the sum of y1 of t plus y2 of t. So in other words, if we add two signals and run them through the system, we better get the same answer as running each individual signal through the system and adding up their responses. If that's true, then our system is additive. Basically, addition works the same on the input and the output. If I put those two properties together, additivity and homogeneity, I get linearity. A system has to be both additive and homogeneous in order to be linear. We can describe that with our system operator notation by combining both scaling of our inputs and summation of input signals to produce scaled and summed outputs. A way to describe that in signals language is if x1 of t produces y1 of t and x2 of t produces y2 of t, then if I scale x1 and scale x2 differently, add those up and create a new input signal, the response that comes out better look like y1 of t scaled by the same scale factor as x1 of t added to y2 of t scaled by the same scale factor as x2 of t. And this is all just a fancy way of describing a behavior that you've known since your early circuit days called superposition. Linear systems have the property of obeying the principle of superposition. And superposition is simply additivity and homogeneity put together. Now, how do we look at a system and its defining equations and tell whether or not, through its system operator or its defining equations, whether it's linear or not? Well, we have to either test its operators for additivity and homogeneity separately. So we have to see if each of these properties holds. And if they both do, then we can declare the system linear. Or we could test the operators for superposition directly by running it through a more complicated test that involves both additions and scaling at the same time. I have to do one or the other, either test it for superposition or individually test additivity and homogeneity. Now let's put that to work. Let's see an example of how we would do that with operator notation. So let's say I have a system and its job is to delay a signal. We'll say it works with a delay operator. Call it D. So my output of my system is a delayed version of any signal I put in. So if I put in x of t, the system's going to put out x of t minus tau. So no matter what signal I put in, I'll get a time delayed version of it, delayed by tau seconds. Functionally, we can represent the operation of this system by whatever function I put in through my system. I'm going to take that function and replace its time argument t with t minus tau to compute the new output. And let's test superposition with that understanding of our delay operator. Superposition says if I can do our system operation to this linear combination of scaled input signals, I should get the same answer as scaling a delayed version of input x1 and adding it to a differently scaled version of a delayed version of x2. Well, let's equation on the left side, run the equation on the right side, and see if in fact we do get equivalence, if we get the same expression out of both of these series of operations. On the left side, a delayed version of ax1 plus bx2 would be take our a times x1 of t plus b x2 of t, and everywhere there's a t, replace t with t minus tau. So we'll take this expression, change the t to t minus tau, and this represents the system operator implementation of the left side of this expression. On the right side, we have a times a delayed version of x1 of t. Well, first we do the delay. x1 of t becomes x1 of t minus tau, and then we multiply it by a. The second factor is b times a delayed version of x2 of t, which would be b x2 of t minus tau. Now we add those two together to create this function a x1 of t minus tau plus b x2 of t minus tau, representing this right side of the equation. And now we test the equivalence. Is this expression the same as this expression? And in fact they are. Since they are, we pass the superposition test. This delay operator is a linear operator. So anytime we have a system that does nothing more than delay a signal by some fixed amount, it's actually performing a linear operation. It obeys superposition, it obeys additivity, and it obeys homogeneity. Now here's a converse example which should be pretty obvious. If I have a system whose job is to take an input signal and square it and provide that on the output, well, we know right off the bat squaring is not a linear operation. And so this should fail the linearity operator tests. Let's just check additivity. Let's take one of the simpler tests to prove this. Additivity says whatever my system operation is, if I do it on the sum of two signals, I should get the same answer as operating on each individual signal and adding them together. That has to be true for the system to be additive, and the system has to be additive in order to be linear. Well, again, let's implement each side. The system operating on x1 plus x2 of t would say whatever's in this operator, parentheses, should be squared. So we'll square x1 of t plus x2 of t, quantity squared, which we know is x1 squared plus 2 times x1 times x2 plus x2 squared. On the right side, we say operate on x1 of t to create x1 of t squared, and then add to that the system operation on x2 of t, which is x2 squared. So we add those together, and we get a non-equivalence here. Here in this case, squaring of the sum created this cross term that we don't have in the individual squared elements. And so a squaring as an operation does not pass linearity because it's not an additive operation. So it's not additive, it's not linear. How about derivatives? Are derivatives linear operations? Well, we're going to need derivatives for our differential equations, so I certainly hope it is, but we can prove it. Again, let's check additivity, and if that passes, let's check homogeneity. Additivity says, again, if we do our operation, in this case take the time derivative of the sum of two signals, we better get the same answer as taking the time derivative of one and adding it to the time derivative of the other. And if we know that is in fact how derivatives operate. If we take the derivative of the sum of two signals, we can replace them with the time derivative of each of the individual elements, which is equivalent to what we have on the other side. And so a derivative function is an additive function. It passes additivity. What about homogeneity? Because at this point we can only say that the derivative is an additive function. We can't yet say that it's linear. It might be linear, but we won't know until we test homogeneity or superposition. Now, superposition is a lot of work, so let's try homogeneity. Homogeneity says, again, let's scale the operation on x1 of t and see if we get the same answer as operating on a scaled version of x1 of t. So for derivatives, we would say is a times the derivative with respect to time of x1 of t the same as the derivative with respect to time of a times x1 of t. And as long as a is nothing more than a numeric scalar constant, which it has to be for our purposes, it cannot be a function of time, this homogeneity test is true. So this derivative operator is in fact both homogeneous and additive, and so it is a linear operator. Now, why do we call these systems linear? Well, linear systems have input-output relationships and characteristics that are typically straight line kind of relationships and pass through the origin. If I put 0 for x in, I get 0 out for y. Some examples of nonlinear kinds of systems or elements, well, one you may have come across is a diode, where their input-output relationship is piecewise linear, but not linear over its whole extent. The relationship between x and y over here on this part of the curve is very different than over here. Another is a true real-life amplifier. We like to model our amplifier circuits as if they were completely linear over all ranges of voltages, but we know that all practical amplifiers are hooked up to power supplies, and so if we put in signals that are too big, so the output excursion gets larger than the power supply, they can't provide any more voltage or any more current than a certain amount, and so they'll clip off. And so again, over a certain operating range, they operate in a linear kind of way, but if we go outside those boundaries, we get nonlinear behaviors. What else can give rise to making a system nonlinear? Well, one surprising element that could is when our circuits or our systems have internal sources, creating, for example, voltage offsets. So this simple static equation, x of y of t equals x of t plus k, just adding an offset, a constant offset to our signal, is a nonlinear operation. Nonlinear because this function doesn't go through 0. And if we tested this simple equation using a homogeneity test, if we did this offset operation on a scaled version of the input, we don't get the same as applying the scaling after we operate and offset the voltage. And we can see that if we play this out. A offset version of a x of t is scale x of t and add k to it. Doing the opposite side, operating on x of t and then scaling it, gives us x of t plus k, and then when we scale by a, we get ax of t plus a times k. We get a different answer for the right side of the homogeneity test. And so a simple offset fails homogeneity, and therefore is not a linear operation. Now, how does this play out in our circuits? What's going to happen is when we have energy storage elements like capacitors and inductors, they may give rise to initial conditions in our circuits. There may be leftover charges or leftover magnetic fields from previous inputs. And so that's going to both make our circuits dynamic, but also going to impose some non-zero initial conditions to the analyses we're doing when we apply a new signal to the circuit or to the system and want to know how is it going to behave. That's going to keep us from using some of our linear analysis tools in order to solve problems that have initial conditions. We can solve non-initial condition problems with our techniques, but we'll have to reserve some other specialized techniques to handle the cases where there are non-zero initial conditions. Now let's kind of review what we've covered so far. We've got two distinctions now between types of systems. They can be static or dynamic. They can be linear or nonlinear. Here's a differential equation that describes a system. Y prime of t plus 1/4 y of t equals 1/2 x of t plus 2 times x prime of t. First of all, is this a static or dynamic system? Well, we would spot these derivatives and know that right off the bat, they force the system to be dynamic. We can't have derivatives and integrals in static systems. So this is a dynamic differential equation, or a differential equation for a dynamic system. How about linear and nonlinear? This particular one is a linear equation. How do I know? Well, we have x of t, we have x prime of t. I don't see any x squared, I don't see any y squareds, I don't see any plus constants here, and so this system is okay. This one is a linear differential equation. Y prime of t plus 2y of t equals x squared of t minus 1. Is this a static or dynamic system? Well, I've got a derivative and I have a time delay. Both of those things, either one of them showing up in my equation, disqualifies it from being static. So this is definitely a dynamic equation. In terms of linearity, the y prime of t is okay. Derivatives are linear operations. 2 times y of t is fine. Multiplying, that's homogeneous. This x squared of t, though, that's a non-linear operation. And so this system is a nonlinear differential equation. Finally, y of t equals 3t times x of t plus 7. is this a static system or a dynamic system? Well, I don't see any derivatives. I don't see any integrals. The y of t has the same argument, time argument as x of t. And so, interestingly, this we would consider a static system. In terms of linearity or not, well, we have y of t. There's no y squares, no x squareds or cubics or higher powers like that. We do have this plus 7. We're adding a constant. And that all by itself is enough to make this a nonlinear equation. And so this is a static nonlinear equation. Now this 3t out here might have made you nervous. And in fact, that did not necessarily make my system dynamic, nor did it necessarily make it nonlinear. It did, however, make it vary with time, makes this whole equation vary with time. And that's our next property that we need to look at. Time invariance and time variance. Time invariant systems, or also known as shift invariant systems, operate like this. If I put some signal x1 of t in, and we've got the different time instances marked on x1 of t, so it's very clear, and that x1 of t produces a y1 of t, then if I put in another signal x2 of t, that's nothing more than a time-delayed version of x1 of t, the signal coming out better look exactly like y1 of t, shifted and delayed by the same amount that my input signal x of t was delayed by. So if I delay here by 3 instances of time to make the new signal, this output better be 3 time instances later than the original one. We should get the same time shift on the input and the output. That's a shift invariant system. Another way of saying that time shifts on the input are seen equally on the output. For time invariant systems, a shift in the input signal produces exactly the same time shift on the output signal. Another way of reframing that and saying the same property is the response of the system does not change with time. If I put the same signal in today and tomorrow and the next day, the system better respond with exactly the same shape response today, tomorrow, and the next day. They're just occurring at different times, but they better have the same size and shape, and everything else about them must be the same. The response should not be varying with time. Now, how do we test system operators to see if they are in fact time invariant? Well, if the system operates on x of t and produces a y of t, then if we let the system operate on a delayed version of x of t, it better produce something that looks exactly like the original output with the same time delay that we imposed on the input signal. Or another way actually to test that is to test if we take an input signal x of t and delay it and then do the system operation on it, we better get the same answer as if we ran that signal through the system first and applied the delay to the result. This is just another way to rewrite the same test here using the combination of operators. So delaying the input and then doing the system operation has to produce the same result as doing the system operator first and then delaying the result. And again, let's try some examples. So if I had a system whose operation was to take your input signal and multiply it by t to produce the output, well, you can't get anything more time varying than that. We're explicitly putting the time and multiplying it by our function. But let's see how this fails the operator test. Here's our operator test for time invariance. Doing the left side here would say take our input signal and apply a delay to it. Make x of t into x of t minus tau. On the right side, we would do our operation on the signal first. So doing our operation means take x of t and multiply it by t. Now we do the second operation stages on each side. Take x of t minus tau, the delayed version, and do the system operation on it, which says we're going to take it and multiply it by t, whatever is in here. So that produces t times x of t minus tau. On the right side, we take t times x of t and do the delay operator. The delay operator replaces every instance of t with t minus tau and produces this output signal. And here we get a non-equivalence on our test for time invariance. And so, as we expected and as we hoped, a very time-varying function like this fails the time invariance test. So this operation is time-varying, not time-invariant. Now it turns out this operation, multiplying t by x of t, is actually a linear operation. It doesn't fail the linearity test, but it does fail time invariance. The derivative operator, on the other hand, is a time-invariant operation. If we do the same test to derivatives, we take x of t and delay it, and then we take x of t and perform the system operator on it on the other side, then do the second layer of operations, take x of t minus tau and take its time derivative, or over here delay the derivative of x of t to produce x of t minus tau, and we get exactly the same function on both sides. So derivatives are both a linear operation and a time invariant operation. And together, linearity and time invariance is a very unique combination, and it's actually the critical combination that we're going to be looking for our systems. One of the consequences of a system that's both linear and time invariant is that it then has a very unique derivative and integral property. If x of t is my input signal, and that produces a y of t signal, if my system is a linear time invariant one, then if I put in a new signal that looks like the derivative of x of t, put that signal into my system, the signal that comes out will look exactly like the derivative of the y of t signal that came out when I put x of t in. So derivatives on the one side produce derivatives on the output, just like scaling and addition do in linear time invariant systems. And as do time delays. All those functionalities operate the same on the input side and the output side of a linear time invariant system. Similarly, running time integrals, if I create a new signal that looks like the time integral of x of t, put that in my system, the signal that comes out looks like the running time integral of my original y of t signal. This is unique to linear time invariant systems. And together, linearity and time invariance put us in this very special class of systems that we call linear time invariant systems, and they're so special that we give them a shorthand name, LTI, linear time invariant systems. LTI systems, linear time invariant systems, can actually be described always by a linear, constant coefficient differential equation. That's an equation that looks like this. We have y of t and some derivatives of y of t and the input signal x of t and some of its derivatives. And the important thing here is all the coefficients out in front of all the y of t terms and all the x of t terms, all these a factors and all these b factors, these have to be numeric constants. That's what makes this a constant coefficient differential equation. It's also a linear equation because we don't have any x squareds, we don't have any y squareds or cubes, and we don't have cross products of x times x or y times y or x derivatives times y derivatives. We just have these simple terms, y of t, its single derivative, its second derivative, x of t, its first derivative, however many we have. And again, the coefficients are all numeric constants. B can't be a function of x, can't be a function of y, or else this would be nonlinear. Can't be a function of t, or it wouldn't be time invariant. And so all we can have are numeric constants in these equations. And we can write those differential equations in a standard form. The way we typically do is put all the y terms and y derivatives on the left side, put all the x terms and their derivatives on the right side. The coefficients that go with the x terms we call b coefficients. The coefficients that go with the y terms we call a coefficients. And we use subscripts for the coefficients that match the order of the derivative of the term they go with. So a and b are constants, they're not functions of time. We use a subscript such as a1 goes with the first derivative of y, b2 goes with the second derivative of x. And we find the highest order derivative on the y side, and that defines what we call the order of the system. And so if we had, for example, just a y prime of t, the first derivative was the highest order derivative we had in our equation, that would be a first order equation. Whatever the order of our equation, we always find the highest derivative of y, and we normalize the coefficients, the a's and the b's, so that that leading coefficient, what would be the an term, we normalize that so that a of n equals 1. So we always have the leading highest order derivative with a coefficient of 1 out in front. Now, we're going to use an operator notation as a shorthand for these linear constant coefficient differential equations. And we're going to use a special flavor of our system operator S. And we'll use it with a superscript, or an exponent if you will, where that superscript k represents a derivative order. So if we put x or y in our system operator x, it's performing a derivative, and the k gives us the order of the derivative. So for example, s squared operating on y of t produces the second derivative of y with respect to t, or y double prime of t. And we'll use a further shorthand of dropping the brackets. So if we put the s operator in front of a y, that implies a derivative of y. And again, the order of the derivative is given by the superscript on the s. So if we were to write out a linear constant coefficient differential equation describing a linear time invariant system, I could rewrite this using my s operator in a shorthand notation, where we'd have s to the n for the nth derivative of y, and whatever intermediate derivatives of y we have here. This first derivative of y times a1 term would be a1 times s operating on y of t. The a0 y of t term would be a0 with no s operator, no derivative. b0 times x of t. The first derivative of x multiplied by b1 would be b1 times s operating on x of t with a first power here. And a second derivative of x times b2 being b2 times s operator operating on x with a second order derivative, and so on. Interesting thing we can do with this operator notation is treat it like it was an algebraic function. And we can literally factor out those operators with their coefficients that go with them and create a combined operator statement here that we're going to do all these operations together to y of t. And then on the right side, all these operations together to x of t. That's a little bit of a hand-waving way of using operator notation. Some of you who are thinking ahead are already recognizing that what we're doing is setting ourselves up for replacing that s operator with Laplace operations. But we're going to hold that thought for now and just look at this from an operator notation way of thinking. So here's some examples of converting a differential equation with the derivative operator notation. If I had a 4y of t equals 8x prime of t minus 2y double prime of t minus 6y prime of t. Well, first we would want to put this in standard form. So we want all the y's on one side, we want all the x's on the other side. So we'll do a little rearranging. Find my highest order derivative of y. Looks like it's y double prime of t, so I have a second order system. And I would want to normalize its coefficient to be 1. So I'm going to divide all these other coefficients by 2 and create standard form of the differential equation. Y double prime of t plus 3y prime of t plus 2y of t equals 4x prime of t. Now, rewriting this with our derivative operator notation, the y double prime of t would be s squared operating on y of t. The 3y prime of d would be 3 times s to the first power y of t plus 2y of t equals 4 times s operating on the x of t. Now, if I have a differential equation describing a system, how do I tell if it's a linear system or not? Whether the differential equation is linear or not? Well, we know one clue. If that differential equation includes a constant term, that then turns it into a nonlinear equation. The other way we can get nonlinear terms is, again, if we have squares or cubics or higher order functions of x or y anywhere in the equation, that will be a nonlinear equation. We can also produce those higher order terms by cross-multiplying x's with y's, so that we get something other than a first order term. So Any place we have x times itself, or y times itself, or x times y, we're going to have a nonlinear term. How we check for time invariance in our differential equation is look at the coefficients. Again, we're only allowed to have constant coefficients in front of our x terms and our y terms. If the expressions in front of any x of t or its derivatives or y of t or its derivatives includes a function of time, that is very explicitly a time-varying function. Can't have that. Interestingly, something else that can ruin time invariance is if our x or our y terms or their derivatives include time scaling, time compression, or time expansion. Those will also make my system a time-varying one because the nature of the differential equation changes with time. So here's some examples. Is this static or dynamic? Well, again, we have derivatives, so automatically it's a dynamic system. This one happens to be both linear and time invariant. All of our coefficients are constants, so it is a linear constant coefficient differential equation. I have no y squares, no x squareds, no x times y's, or any of those cross kind of terms, and no constant added to it. So this is both linear and time invariant. How about this one? Well, we've got a couple suspicious things going on here. First, we have this y squared. Well, that's a tip-off. This is not a linear system anymore. This term is fine. The leading coefficient is fine, but the y squared makes this nonlinear. Over on this side, we have a constant coefficient out in front. We do have a time shift, though. It turns out that this time shift is okay. It doesn't ruin linearity, and it doesn't ruin time invariance. The y squared messes up linearity, but this is a nonlinear time invariant system. Okay to have time delays. It's time compressions and expansions, time scaling that we're not allowed to have for a time invariant system. Here's another example. This term looks fine. This term looks very problematic. This term alone by itself will make this differential equation time varying for two reasons. Because I have a 4t out in front, and because of this 2t time argument. Either one of these individually would make this a time varying function, not time invariant. Them together just makes it more so. Over here we have 3x of t. That's fine for linearity and time invariance. But I have a constant 7 addition, which makes this a nonlinear system. So this is both nonlinear and time varying. And finally, here's a second order system, y double prime of t. We have a time shift again, but we know that's okay. That term looks okay. There's no t out in front, there's a constant coefficient, but there's a cross multiplication between y terms. And so this particular function would be time invariant, but nonlinear, and nonlinear due to this product of y and y prime of t. So that's how we can look at the differential equation describing a system and tell whether or not it is a linear time invariant system. That's the kind we're looking for, ones that are both linear and time invariant.